if somebody were to say, hold a bowling ball over your head, you might reasonably get a little nervous. If they were to hold it high above your head, you would also be reasonable to get more nervous. But why? It's not moving in either case. Well, we understand that when the bowling ball is high up, it has more potential to do harm to us. It has the potential to do work, more work, in fact, when it's up high. This idea that the height of some object impacts some ability to do work, or the amount of energy that thing has, is tied to something we call gravitational potential energy. Gravitational potential energy will consider energy of a system. Now that's a little different from how you might have seen this definition before. Energy for a system, not for a single object, but for a system that includes a couple different objects at least that interact through a gravitational force. And really we're just going to care about any system that has a decently sized gravitational force interaction. So between two people, probably we don't care about the gravitational potential energy because the gravitational force is going to be tiny. Between the Earth and a person, now we care about both of those. So this is going to be energy that's associated with separation between two parts of a system that want to snap back together due to this gravitational interaction. And the further apart we get these objects, the more gravitational potential energy we have. It takes work to separate objects that are attracted to each other by a gravitational force. The amount of work that it takes is going to be exactly equal to the amount of potential energy, gravitational potential energy, that we have in our system. And if we let these two things fall back together, the amount of kinetic energy we're going to get as they fall will be equal to the amount of work done by gravity, which will be equal to the amount of gravitational potential energy that they had when they started, or at least how much it changes. We have a couple ways to calculate gravitational potential energy. And so first we'll see this equation here that doesn't actually get used nearly as often as the second one. This is the general equation. It can be used for any situation, any two objects that are attracted to each other by a gravitational force. So we have a few different terms in here. We have G, that's the universal gravitational constant. That's on your equation sheets. 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. More on that to come. We have the mass of our two objects. So if we're looking at, say, a bowling ball and the Earth as being the two objects that are interacting by gravity, we'd have the mass of the bowling ball and the mass of the Earth. And then R is the distance separating those. We're actually going to look at the distance separating the center of mass of each of these two objects. So from middle of object to middle of object, that's the distance that we're looking at there. Now, as I said, that works in any situation, but if we have an object that's moving from place to place a fairly small distance compared to, say, the size of the other object, it'll turn out that we need it to be a small enough distance that the value for acceleration due to gravity doesn't change appreciably. Then we have a simpler way to look at these calculations, and that's the second equation. So if we just care about how much gravitational potential energy changes when an object moves from one spot to a different spot relative to that second object, we can use this second equation then. M is going to be, in general, the mass of the small object. So we'll typically have the Earth as our big object, and then a ball, a box, a person as our smaller object. This will be the mass of the small object. G is the gravitational acceleration. On Earth, we'll use 9.8 meters per second squared, or 10 for the the multiple choice section of the AP test. And then last up, we have this delta Y. Delta Y is going to represent either a change in vertical position or the difference in vertical position relative to some reference level. So with these problems, we'll just make a decision when we're using this equation. We'll make a decision about where our reference level is. We'll say that dashed line represents the reference level. And then if we have our object, our small object, up above that location, we're going to say it has a positive value for UG, for gravitational potential energy. And then if it's somewhere below that, we'll have some negative value for UG. And then right at the reference level, we'll have UG is 0. We'll also, up here, have some distance delta y, or distance delta y here, with the direction mattering here. So an upward arrow, we'd have a positive direction on this one, and so we'd end up with a positive gravitational potential energy. We generally don't care what the value is at any single moment in time. We're typically going to be more interested in how that gravitational potential energy changes over time, because if that changes, that must mean some other energy type is changing as well. Maybe an object falls and it loses gravitational potential energy, but it's getting faster, so it gains kinetic energy. Those will be the problems that we typically work using that second formula. So let's do one exactly like that. We have a ball that's dropped from rest from a height of 4 meters. What would speed be when it reaches the ground? So the idea on this is that if we have no work being done on our system, our change in energy, which is equal to the work, is going to be 0. So the amount of energy in our system will stay the same if work done on that system is 0. Now in this case, let's define our system as the ball and the earth. And so we have a force on the ball, downward from gravity, from the earth. That's an internal force, so that's not doing work on our system, that's work inside of our system. No external force there. We'll assume no air resistance, because that's the usual on the AP test. If they don't say otherwise, assume no air resistance, or air resistance is negligible. So no force from that. So the only forces we have are internal forces, which means no work done on our system from outside, so no change in energy. So whatever energy we start with has to be the same as the energy that we end with. So we might write that out as energy initial equals energy final in this case. Initially, what kind of energy do we have here? Well, we've got our ball at rest, so no kinetic energy, it's not moving, but it's up high. Let's say that our ground is going to be the reference level on this. So using the ground as a reference level, we start out at some position above the reference level, which means we start out with some positive gravitational potential energy. So we'll say that our UG, and we have the delta there just to remind ourselves that this is just how different it is from what it would be at the reference level. That's our initial energy. Final energy, we'd have just kinetic energy. It gets down to the ground level, so we're going to have 0 gravitational potential energy there, and it's going to be moving when it hits the ground, so we'll have kinetic energy. Now we can set up an equation, we can substitute expressions for each one of these values. So we have m times g times delta y equals the gravitational acceleration, or gravitational potential energy. 1/2 mv squared is equal to the kinetic energy. And at this point we know everything in that equation, so we can plug in and solve. So we have a 2 kilogram mass. We have gravitational acceleration at 9.8 meters per second squared. And we have a starting height of 4.0 meters. And that's equal to 1/2 times our mass, 2 kilograms, times the speed squared, and we're looking for speed on this one. So we want to figure out how much energy we started with. So that's 2 times 9.8 times 4. So 2 times 4 is 8, times 9.8, 8 times 9.8, 78.4, and that'll be in joules, 78.4 joules of energy. Equals 1/2 times 2, so that's just 1 kilogram, times v squared. So we'll divide both sides by 1 kilogram. Joules, it turns out, is the same as kilogram meters squared per second squared. So if we divide that by kilograms, we're left with meters squared per second squared. We'll square root it and end up with meters per second. So 78.4, then we're going to square root that, or take it to the 1/2 power, to get our speed of 8.85 meters per second on this one. All right. Now, what if we change the situation a little bit? So now it's going down a frictionless ramp. It turns out nothing actually changes in this one. As long as we don't have friction, we still only have a couple of forces to consider. First, we have gravity, and that's an internal force if we define our system as the block and the Earth. So we don't have to worry about that changing our amount of energy. No friction. The only other force on the block would be the normal force, but normal force is always going to be perpendicular to the direction that the block moves. If it's sliding along the ramp, normal force is perpendicular to the ramp, so the work there would be 0. FD cosine theta to get work. Theta is going to be 90 degrees if they're perpendicular, and so we get 0 work. So again, we have a situation where our starting energy in our system equals the ending energy in the system, and exactly the same thing happens here. We start out with gravitational potential energy, mg delta y. We end up with kinetic energy, 1/2 mv squared. Now you might notice here, and actually in the last problem, that there is an m on both sides. So if we divide both sides by m, we get g delta y equals 1/2 v squared. And if we plug in values for each one of these, we've got 9.8 and 4, and solve for v, and we get exactly the same result we did before. 8.85 meters per second equals our speed. All right, one more here. This one, we've got our block initially at ground level, and it's going to be sliding up this curved ramp going up there. It's going to stop at some point and then start to slide back down, and the question is, how far does it slide before it stops? Well, again, we have no friction, we have gravity, and if we think of our system as being the block and the Earth, then gravity is an internal force. We've got a normal force on this block, but always perpendicular to the direction that block is moving, so it doesn't do any work on the block. We have no outside forces then. So again, our energy that we start with within the system of the block and the Earth is equal to the energy we end with. This time though, we start with our block moving. So we have kinetic energy initial, and I'm just going to put a K naught there. And then it's not up high. Let's say that the horizontal surface is our reference level. So anything above that, and it's going to have gravitational potential energy. So no gravitational potential energy to start with, but eventually it's going to get up high and it will stop. So it'll have nothing but UG, delta UG, when it gets up to its highest point. It stops and it's up high. Stops, so no kinetic energy. Up high, so yes, gravitational potential energy. All right, the formula is exactly the same as it was before, just reversed. Make that V naught squared, and then mg delta y. Again, it turns out we don't need our masses, so we'll have 1/2 times the speed, which is given as 5 meters per second squared, equals 9.8 meters per second squared times delta y. So we'll do 5 squared is 25, times 1/2 is 12.5, and then we'll divide both sides by 9.8. So 12.5 divided by 9.8 to get delta y is 1.28. We do meters squared per second squared divided by meters per second squared gives us just meters equals delta y. Lots more problems like this to come. Gravitational potential energy, kinetic energy, and then there's a third one we'll deal with called spring potential energy, are all going to play together very nicely in these problems. The only time we won't have this situation where E naught equals E, where our starting energy and ending energy are the same, is if we have work done on our system. So we'll have to look at problems like that as well. Thanks very much for watching. If you learned something, I'd encourage you to subscribe or like this video so it shows up for other people as well. Thanks again.